Welcome viewers to the online series of lectures for the course of linear algebra. The course code for this course is MAT212. The first lecture will be based on basic operations in matrix algebra. The basic operations. So an M times N matrix is an arrangement of arrays like this. A11, A12 all the way up to A1n, A21, A22 all the way up to A2n, AM1, AM2 all the way up to AMN. As you can see here that in this arrangement there are M rows. These are the rows. This is the first row. This is the second row. This is the mth row. And there are n columns. So this is the first column, this is the second column, and this is the nth column. So the entries, these are called the entries of the matrix. So a general entry in such a matrix is denoted by Aij. So this is what we write here. The numbers in an M times N matrix are called matrix entries, so that this is an entry, this is also an entry, and are denoted by Aij with I varying between 1 and m, the endpoints included, and j varies between 1 and n. Okay. J is called the column index and I is called the row index. I is the row index and J is the column index. Okay. Okay, so let me erase everything so that Aij is the entry which appears in the ith row and jth column of the underlying matrix. Jth column of the matrix. Okay. So here is the matrix. Suppose the entry is situated somewhere here, Aij, and this is situated so that it belongs to the ith row and jth column. Okay, so from 1, 2, 3 all the way up to jth column you go, and 1, 2, 3 all the way up to ith row you go, and the intersection of the ith row and j column will give you the position of the entry Aij. Such a matrix is denoted by simply A, big A, or by Aij. This way the entries of the matrix, the underlying matrix, are manifest. It means that Aij is an entry of the matrix A. A 1 times n matrix is called an n-dimensional row vector, okay, because it consists of only one row, but in this matrix there are n columns. So a row vector is written like this: a1 all the way up to an. As you can see here is that there are n columns here and there is a single row. Okay, now and m times 1 matrix is called an m-dimensional column vector. And a column vector is given by a single column b1 all the way up to bn. You can immediately see here that there are m rows here and one column in the matrix P. Okay. Now we define addition between matrices. Addition of matrices. So two matrices can be added to each other if they are of the same size. Okay, it's obvious because otherwise we cannot define addition between them. So a matrix denoted by Aij and another matrix denoted by Bij are added to give a new matrix Sij, where the additions are entry-wise. That is, Sij is equal to Aij plus Bij for all I and j. Okay, here is an easy example of matrix addition. We have a 2 times 3 matrix, 2 1 0 1 3 5. We have another 2 times 3 matrix given by 1 0 3 4 minus 3 1. So we add these two matrices by adding the corresponding entries. So 2 gets added to 1 to give 3, 1 gets added to 0 to give 1, 0 gets added to 3 to give 3. We have 5, we have 0, we have 6. Okay, now the operation of scalar multiplication of a matrix by a number, scalar multiplication of a matrix by a number. Okay. This is given by C times a matrix Aij is equal to a new matrix Bij, where the entries of this new matrix are given by Caij for all ij. For example, we have this 3 times 2 matrix 0 1 2 3 2 1, and we are multiplying this 3 times 2 matrix by a scalar 2, a number, to get the new matrix by multiplying each of these entries by 2. So we have 0 here, 2 gets multiplied to 1, 2 gets multiplied with 1 to result in 2. Similarly, we have 2 times 2 here, 4. We have 2 times 3 here, 6. Then we have 2 times 2 here, 4. Then we have 2 times 1 to give 2. The numbers are referred to as scalars. This is a scalar, whereas this is a matrix. Numbers are referred to as scalars. Okay, good. Now the most important operation, which is a bit tricky, is called matrix multiplication. Okay, so it is important to note here is that not a matrix can be multiplied with any other matrix for a given size. What I mean here is that if I am given a 2 times 1 matrix and I want to multiply it with a 7 times 9 matrix, I won't be able to do so. So the matrices under this operation must be compatible with each other with respect to multiplication. Okay, they should be multiplication compatible. So what does that mean? The column of the first matrix should be the same as the row of the second matrix. So we can always multiply an n times L matrix with an L times S matrix, and the size of the resulting matrix will be n times S. Okay, in terms of sizes, these equalities hold in terms of this equality holds in terms of sizes of the corresponding matrices. Okay, now suppose A is this matrix Aij and B is another matrix Bij. Here I runs between 1 and m and the integer j runs between 1 and n. Okay, so this row index runs between 1 and m, and the column index runs between 1 and n. Okay, so the size, which means that the size of this matrix A is m times n. Okay. Similarly, for B, I runs between 1 and n, and j runs between 1 and L, so that the size of this second matrix is n times L. So like I said before about the compatibility of matrix multiplication, we see that A can be multiplied with B, since the uh, the the column number for A is n, and the row number for B is n as well. So A times B will be a new matrix called Cij, where Cij is equal to the sum of the following products: Aik, Bkj, and k runs from 1 to n. Okay, so these are the entries of this new matrix Cij. Okay. So this is the size of the first matrix, this is the size of the second matrix, so n times L. So the size of the resulting matrix should be m times L. So here I should vary between 1 and m, and j is supposed to vary between 1 and L. Is the m times L is the size of AB. Okay, so now I give you an example of matrix multiplication. Suppose I have a 2 times 3 matrix given by 0, minus 1, 2, 3, 4, minus 6. In order to have a well-defined matrix multiplication, we should have the later matrix to have 3 rows, right? Because the first matrix has 3 columns. Suppose we have this 3 times 2 matrix, 1, 2, minus 1, 3, 4, 2. Okay, so this one is A and this one is B. Okay, the size of this first matrix is 2 times 3, and the size of this second matrix is 3 times 2. So the resulting matrix will be of size 2 times 2. Okay, so the resulting matrix we call is just A times B, which we call Cij, and this will be a 2 times 2 matrix, which follows from the discussion conducted earlier, and AB is just C11, C12, C21, C22. Okay, there are 4 entries here in this matrix. So C11, so remember that we wrote this sum of the product expression Cij as Aik Bkj, where k runs from 1 to n, right? So C11 is going to be A11 B11. So we keep this one and this one at the two far ends fixed and change this common index k from 1 to n. So the second entry is going to be A12 B21, right? And the third entry is going to be A13 B31, right? And n here is 3, right? This common number, which is the number of rows in the number of columns in the first matrix and the number of rows in the second matrix. This is 3. So k runs from 1 to 3. So this is C11, and by putting the values of these entries, we see that this is 0 plus 1 plus 8, which is 9. Then we find C12. So again, we put this A and B and fix these two indices at the two far ends, and then change this variable index, which is common, okay, which is the same here in these two slots. So it runs from 1 to 3. So again 1 1 here, then this is 2 2, and then this is 3 3, okay. So we have A11 is 0 and B12 is 2, A12 is minus 1, and B22 is 3. When you multiply one with the other, you get minus 3. And finally you have A13, which is 2, and that gets multiplied with this 2, which is B32, right? So the final result is minus 3 plus 4, which is 1, okay? Alright, so now similarly we can find C21, which is A21 B11. Then we have A22 B21, and finally we have A23 B31, okay. We see that this is 3 minus 4 minus 24 is minus 25, and finally we have C22, which is A21 B12 plus A22 B22 plus A23 B32, which is equal to 6 plus 12 minus 12 equal to 6, okay. Good. So the product of these two matrices A and B is thus going to be a 2 times 2 matrix, which is 9 1 minus 25 6, okay. All right, we stop here. We end the first segment here. Thank you for attending the first segment of the first lecture for the course of linear algebra.